Okay, in section 2.4 we talk about directional limits, and directional limits don't just have to happen with functions in one variable. Like you can think of the temperature at a position on Earth as a function of that position. And as you're traveling around the Earth, maybe you're going west or maybe you're going northeast or something, and as you reach a point, your temperature is changing, and that direction, that limit of temperature as you're going in that direction would be a directional limit. In functions in one variable, we only have two directions to worry about, which is really nice. We only have to worry about coming in from the left or coming into the right, from the right to a point. So let's just state that a little bit more explicitly. There are two directional limits for functions in one variable. Okay, so if we have a function f of x, we have two directional limits. We have the left limit and the right limit. Okay, and we'll write these as the limit as x approaches some value c, but I'm going to put a superscript with a minus on it. That means I'm coming in from the negative side. F of x. This is the limit of f of x as x approaches c from the left, from the negative direction, from the negative side. And notation wise, it's probably pretty obvious, but the limit from the right, instead of having a little superscript of a minus, we put a little superscript of a plus, f of x, and then we've got, this is the limit of f of x as x approaches c from the right. Okay, so let's draw a picture about those two things. This will look pretty familiar probably, because we've drawn similar pictures to this for a while now. So I'm going to have a disconnected function, and the disconnection is going to happen at c. And let's say this point here is at c comma 1 and this point's at c comma 3. Oops. Then how this limit stuff works, if I'm coming in from the left, the output values are approaching 3. If I'm coming in from the right, the output values are approaching 1. So we can write things down as the limit as x approaches c from the left, from the negative side. The outputs of f of x, they're going to equal 3. They're going to get closer and closer to 3. The limit as x approaches c from the right, from the positive side, if I'm coming in from the positive side, the output values are approaching 1. So even though the limit doesn't exist at c because they're different from the left and from the right, from the left we are approaching a value, and from the right we're approaching a different value. Those two limits, the left-hand limit and the right-hand limit, do exist, and in this case they are 3 and 1 respectively. Okay, so this concept isn't necessarily that difficult, especially since we've seen limits already. We've just got to sort of focus our attention on one side or the other of the point C, right? You can think of it as, well, When we're taking a full limit, I sort of cover up this point at C. I get rid of that part of the graph, and I don't know what's happening at C specifically, right? And if I don't look at that part of the graph, it doesn't look like these two lines are connected, so we say that the limit doesn't exist. If I'm coming in from the left, I cover up all of the stuff on the right. If I cover up all of the stuff on the right, what's it look like this function's going to be doing? Well, it looks like it's getting close to 3. So my limit from the left covers up everything on the right and the point itself, and we say, well, it looks like the function's going to be 3. If I was taking the limit from the right, I'd cover up everything on the left and say that my function looks like it was approaching 1 on the left, right? So if I cover up all of this stuff from the right, I've covered up everything on the left and the point itself, it looks like my function is going to be 1. Okay, so that's what these limits from the left and from the right are, these directional limits. Like I said earlier, you can have directional limits if you have a function in more than one variable. Like you have 2 variables, you've got a function that lives on the complex plane or something, or on the xy plane, right? I've got my inputs are the plane here, and I've got this curve or surface above the plane that does some weird stuff. Right, I've got this surface that lives above the plane. On the plane, on that, I could follow points. I could sort of come in from certain directions on this plane and take limits there. We do that a little bit more in Calc 3, but the idea is you're coming in from a certain direction. In Calc 1, we just come in from the left or the right because we only have one direction that we can travel. We can travel left or right. I guess 2 directions we can travel. But they're all on the same line. They're all on that x-axis. Okay. Let's write down the specific definitions for these limits. And it's going to be really similar to our definition in general of a limit, right? In general, in a limit, let's write down the limit as x approaches c of f of x equals L means for all, the upside down A means for all. Let's just actually write out for all. For all epsilon bigger than 0, there exists delta bigger than 0 such that if 0 less than the absolute value of x minus c is less than delta, right? If my inputs are close enough to c, my x values are close enough to c within delta of c, then the outputs f of x and the limit are within epsilon of each other, right? My output tolerance is guaranteed as long as I've got my inputs close enough together. Okay. This part of this limit right here on the number line says if I'm here at C, I can go to the right by delta, or I can go to the left by delta. And as long as I'm in this whole thing, this thing is satisfied, right? I don't want that point at C specifically, so I avoid the x minus c equaling 0. But as long as I'm in this interval here, I guarantee that my outputs are close together. So for the right-hand limit, let's do the left-hand limit first. For the left-hand limit, if I want to come in from the left, right, I want to be in this area, and then I still want to guarantee that my outputs are close to epsilon. I don't care what happens on this side, right, for the left-hand limit if I'm coming in from the left. So instead of having this absolute value inequality, we're going to have an inequality that corresponds to having an x value that's between c and c minus delta. Okay. What I want then is I want the distance between x and c to be less than delta, right? But I want c to be bigger than x. So for c to be bigger than x and the distance between them to be less than delta, we need c minus x to be less than delta, right? The distance is the positive difference between the things. If we're guaranteeing that c is bigger than x, then I want c minus x to be less than delta. And I also want this to be bigger than 0, right? If I had taken an x over here, then the c minus x would have been negative, right? C minus x for these two would have been negative c minus x. For these two, it's a positive c minus x. I want to be on the left. I want to be on the left is what this part of the inequality says, and I want to be within delta of c is what this inequality says. X is left of c. C is within delta of x. Okay. So our left-hand limit is going to read very similar to this. I want it to read, we say, the limit as x approaches c from the left, f of x equals L if for all epsilon bigger than 0, there exists delta bigger than 0 such that if 0 is less than c minus x is less than delta, then the absolute value of f of x minus L is less than epsilon. Okay, I still want my outputs to get really close together, so I still have my epsilon tolerance, and I don't know if the function's increasing or decreasing, so I still need the absolute value around the outputs because I don't know which one's going to be bigger. But I do know that I'm coming in from the left. So if coming in from the left means that c should be bigger than x, so this difference should be positive, right? It should be positive so that it's bigger than 0. And I still want the distance to be less than delta, so I want c minus x to be between 0 and delta. Okay, and that's our definition of a limit from the left. The same ideas play out for the limit from the right, so let's just write that out. The limit as x approaches c from the right, f of x means equals L, means that for all epsilon bigger than 0, there exists delta bigger than 0 such that if 0 is less than something is less than delta. Okay, now I want to come in from the right, so I want x to be bigger than c. So I'm going to take x minus c, and that's the distance from x to c as long as x is bigger than c. And I want x to be bigger than c, so I want x minus c to be bigger than 0. And I want this distance to be less than delta, so I want this inequality, right? I've just switched the x and the c from the left hand, which means I'm coming in from the other direction. So if my inputs are close enough to together, then the outputs f of x minus L are close enough together. Okay. So that's the definitions of these things and the picture of what's going on. I'm gonna get another short video together where we actually compute some examples of these things, and we're gonna do some other special limits as well. And the next video.